Okay, so in today's lecture, let me just change this pointer option. We're mostly going to focus on Fourier transforms. And so this is meant to be review, but for some of you, there might be some new material. So feel free to stop me whenever you'd like, and we can certainly focus on topics that are more interest to people. Oops. Okay, so basically we're going to go over the expressions for the forward and inverse Fourier transforms in both 1D and 2D. We're going to talk a little bit about the units that are used. Typically, we think of doing Fourier transforms, at least in this class, in either time or space. We're going to spend quite a bit of time giving you an understanding of what the spatial patterns associated with what's called K-space are. So K-space is another name for the Fourier space. Especially for imaging, it's good to have a understanding of what those patterns are. We're going to also look and see what happens when you make modifications in the Fourier transform, how that affects the associated image. And that will be useful for sort of the homework 4. There you do some exercises, you're led through some exercises on Fourier transforms. And so some of the images we go over today will look very much like the images you'll do in homework 4. After we get that basic understanding, we're going to compute. Let me just make sure we are recording. Compute some basic Fourier transforms, getting working knowledge of some basic Fourier transform pairs, and also apply basic Fourier transform properties. Okay, so for the supplementary session 1, we talked a little bit about images, and we talked about how we could have discrete time images where we index the image values. Here's a signal indexed by integer values. Or else we could have a 2D image, and here you would have the integer index n and m, and so we basically have a 2D image, but it only has values at discrete pairs of these integer values. And then typically what we're interested in imaging is something that we consider to be continuous, either time. So this might be, for example, a waveform of someone's speech or some sound, or we imagine some continuous object. And so here we would index as time, where time is a continuous variable, or we might think of something x and y, where we consider x and y both to be continuous variables. And last time we talked about writing these as a function of a summation of weighted either Kronecker delta functions for images or Dirac delta functions for continuous, okay? So that was sort of just to remind you what that looked like is, for example, for a 1D function, we would write this as any function g of x could be represented as a sort of a sum or some integral of little, in this case, rectangles, where we're showing sort of a discrete approximation. In the limit, these would turn into Dirac delta functions. And so saying any g of x continuous can be written as a summation of weights multiplying Dirac delta functions at different locations. So today we want to look at a different way of how do we represent a signal. Later in the course, we'll talk more about basis functions, but essentially we're switching from, when we think about changing from Dirac delta functions to Fourier functions, we're switching essentially the basis functions that we use to represent our signal. So let's say we have this signal here that goes down and up and up and down. And so if you were just look at this signal and someone were to give you this signal to look at, you might say, well, that's a sort of complicated looking signal. And to represent the signal, you might think I need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, maybe like 16 points to really sample the signal properly if you just knew nothing about the signal, okay? But if you knew the signal were composed of these different sinusoids, okay, and you said, well, I know that this signal here is composed of different sinusoids at different frequencies, and then all I really need to know is the weights of these different sinusoids. So for example, this weight here says that I'm going to use this amplitude here for this frequency. This has a bigger weight represented by this longer black bar. So as you can sort of see, this has a bigger amplitude. And this one here has a smaller amplitude. And so it's sort of weighted by a smaller, it has a smaller amplitude sinusoid. So it turns out if you add up all these different sinusoids with different weights, you get this complicated looking signal. And essentially these weights then are essentially representing the Fourier components or the Fourier weights. And so this collection of weights at different frequencies is what we would call the Fourier transform of this signal. And this is a 1D signal. So this is a 1D Fourier transform. Okay. So that's the basic idea. We're just basically trying to represent our signals and images as a sum of sines and cosines. So let's go over the definition of Fourier transform to review. So basically, we take our signal, g of t, we multiply it by this complex exponential, in this case, e to the minus j 2 pi ft. F is our frequency here. And we integrate that over all of time. And if we put f in here, then that gives us the Fourier transform at some value. So we call that g sub f. Okay, this is little g. Typically, we'll use big G to represent the Fourier transform. We can also write this as this is the Fourier transform of g of t. Now, the amazing thing about this is an invertible process. At least for all the functions that we're going to look at, we can invert this process. So given g of f, we can go back to get g of t. Okay. So, and the expression for that is quite simple. We take our g of f, and we multiply it by a complex exponential that has exactly the same form of what we used before, except here it was negative and here it's positive, okay? And now since we have a function of f, we integrate over df and we get back our function g of t. So this could also be represented as the inverse Fourier transform of g of f. So in 1D, we can already start talking about coordinates. So oftentimes, and for example, when we talk about RF pulses in MRI, we might think about something as a function of time, okay? And we might want to understand the Fourier transform of that time-dependent function. And so we call that g of f. And here, t is in seconds, for example, and then f, our frequency would be in cycles per second or hertz, okay? Now, if we do spatial coordinates, then for example, x would be in centimeters and kx would now be a spatial frequency in terms of cycles per centimeters, okay? So in this, for our nodes, we will use k sub x to represent spatial frequency. The book uses u and v, but we will stick with kx and ky for spatial frequencies. So anything that's in space will be in units of like millimeters or centimeters. And then the k sub x will just be how many cycles of the sinusoid or cosine are there per millimeter or centimeter or meter, depending on what spatial scale you want to be at. Okay, as Professor McVeigh discussed in class, a very useful thing to keep in mind is Euler's formula, which some have said is one of the most beautiful theorems in all of math. In this case, j represents the imaginary number. So j equals square root of -1, okay? So we have e to the j theta equals cosine theta plus j cosine theta. And since this is actually a complex number, so basically it's got a real part, cosine theta, and imaginary part, sine theta, okay? It has a magnitude of 1 because cosine squared theta plus sine squared theta equals 1. And so we can also, this has the general form of any imaginary number, or any complex number can be written in the form x plus jy, or magnitude times e to the j theta. And so this form is actually quite useful to keep in mind. So this leading term always gives you the magnitude of this vector, okay? In this case, z, the magnitude is 1. And e to the j theta, this theta term just tells you what angle the vector is making. So this is the theta term here with your x-axis, okay? Where theta positive goes counterclockwise, and theta negative would go clockwise. Okay. Okay, so as Professor McVeigh went over in class, it's useful then to write out the 1D Fourier transform. So we have g of x equals this, and we can use Euler's theorem to expand this out as cosine 2 pi kxx minus j gx sine 2 pi kxx. Okay, where the cosine of this negative term is why this is positive, and this minus sign becomes because of the sign is an even function. So sine of minus j 2 pi kxx equals minus sine of 2 pi kxx. So it's useful to look at these terms individually. So this is essentially taking some function g of x and multiplying it by a cosine of some spatial frequency and then integrating it. So for those of you who may remember some of your linear algebra, this is essentially an inner product or a dot product in continuous space. So it's sort of saying, how much does g of x look like this cosine 2 pi kxx? Okay. And so some things to sort of cover even at this early stage is cosine 2 pi kxx looks like this. And if kx is the spatial frequency, then 1 over kx represents the distance or the period between the peaks. Okay. So the period of anything with this form 2 pi kxx is just 1 over kx. And so if our function looks a lot like a cosine, then this term will tend to be big. Now the cosine obviously just is, sort of has its peak at 0 and periods of that. So we also need the sine to sort of capture functions that are slightly shifted. And so that's why we need the sine term here. And so this is the part of gx that looks like sine of 2 pi kxx. And so with the sine and cosine, we're able to pick up sort of any shifts of the signal between the cosine and sine. So that turns out to be sufficient to capture signals that are shifted in time or space. Okay, so if there's no questions, let me see, looking at the chat, there doesn't seem to be any questions so far. So let's go over the Fourier transform in 2D. So g of kx ky equals the Fourier transform of this two-dimensional object here. And that can be written as a double integral of gxy times now this e to the minus j 2 pi kxx plus kyy. And that's integrated over dx dy. And as I said before, prints and links will tend to use u and v instead of kx and ky. I'm not sure exactly why they make that choice, but we will stick to kx and ky since that is definitely used much more often in the MRI literature. And so it's good to get used to this terminology if you're going to go into this area and do more work. So this is the forward Fourier transform. And then we also have the inverse Fourier transform, which can be written as follows. We take our function of kx, ky, we multiply it by this complex exponential. Notice here we had a minus sign, here we don't have a minus sign. And now we integrate over dkx and dky. And assuming that sort of these are nice functions, we can get back gxy from its Fourier transform. So this is very powerful because what we do in MRI, as we'll cover in a few lectures, is we actually acquire, this is the signal we actually acquire, gkx ky. Okay, so we actually acquire the data in Fourier space. And so once we have that data, then it's just a matter of doing this transform to get back to the image, the underlying image that we care about. Okay, so in fact, given any object that we might want to image, this formula is essentially what MRI does. Okay, it actually carries that out using basically just physics and the measurement process. Okay, so it is really important then to sort of get an understanding of what this term looks like. Okay, so we have e to the j 2 pi kxx plus kyy. And now, so we can use Euler's theorem to say this is a cosine of 2 pi kxx plus kyy plus j times sine 2 pi kxx plus kyy. Now, if you haven't looked at things like this before, it's useful to take a step back and just sort of take some very simple cases to understand what do these things look like. Like, what does cosine 2 pi kxx plus kyy look like? So let's take the case where, let's say, ky equals 0. So we don't have to worry about this term. So we're just left with cosine 2 pi kxx. So that would look, this would be here, okay? So this is a function that only depends on x, right? So for a given value of kx, it only depends on x. So it's only going to vary along the x-axis, so in this direction, okay? And so basically along the y direction, you see there's no variation, right? And what I'm representing here are sort of the peaks of cosine. So we can think of, in 2D, it's sort of hard to draw, by hand, a two-dimensional cosine. So oftentimes we'll just draw these lines to indicate where the peaks are. In this case, the peaks are 1 over kx apart. And essentially you can think of this as a two-dimensional cosine wave that's varying in x, but along y, it's the same. So it's basically this wave that varies along x. Similarly, if we assume that kx equals 0, then we get cosine 2 pi kyy. So now there's only dependence on y. So the peaks only vary as we go. But basically, we see the peaks as we vary along the y direction, and there's no variation along the x direction. Okay. Now, in general, we can have both kx and ky, and so that could be vary in any direction, depending on what the values of kx and ky are. And it turns out that the spacing between the peaks now is given by 1 over the sort of kx squared plus ky squared, so the magnitude of the k vector. Okay, so this is just the Pythagorean theorem. So if you have some kx, ky, now obviously if ky equals 0, this just turns out to be kx. And if kx equals 0, this just turns out to be ky. But in general, you're sort of taking essentially the hypotenuse of your kx and ky values. So this turns out to be fairly useful to remember, because when you, let's say you're given some pattern like this, like you're shown a wave that has this sort of pattern. One point you can do is if you just draw the perpendicular to those wave fronts, that will give you the direction of the k vector. Okay, so for example, this theta is showing that this is the theta that you would have. So this theta equals arctangent ky kx. And so this is actually the direction of the k-space vector. So essentially, the nice thing about if you draw in k-space, the direction of that vector tells you the propagation direction of the wave. So if you imagine waves propagating in this way, they're propagating along the direction that's indicated by your k-space vector. Okay, and we'll go over that a little bit in some examples. Okay, so let's take a look at a few examples from the book. This is figure 2.5, and this is 6 instances of a sinusoidal signal s of xy equals sine 2 pi u naught, and in this case, we would replace it with kx plus v naught y, and this would be our ky. And we're gonna look at various values for, in this case, kx and ky. So here you notice that ky equals 0, right? And so we know that there's not going to be any variation in the y direction. And in fact, that's what we see here. There's no variation in the y direction in any of these images, right? So there's only going to be variation along the x direction. And here we have kx equals 1, kx equals 2, kx equals 4, right? And so you notice that, remember, the period is just 1 over this number. So here the period would be 1, the period here would be 1/2, and the period here would be 1/4. And you do notice that sort of the distance between these troughs or these peaks. So here's the distance between the troughs, here's the distance between the peaks. It is becoming, those peaks and troughs are becoming closer together. That period is becoming smaller as we increase the spatial frequency. All right. So this is a very important example to keep in mind as you're looking at different images. The other thing you can think about is we can play this game where we keep this mu naught, this kx equal to 4 in all cases. So this is 4, this is 4, and this is 4. That means the period along the x direction is always going to be 1/4. So let's see if that's the case. So this, if I go from this trough to this trough, okay, that's the same distance as from here to here, right? And that's the same distance as from here to here. So the period along the x direction is the same for all these images. Now let's see what's happening in the ky. The ky says that the period here is 1 in the y direction. So maybe that's from here to here, right? This is from a trough to trough, that's a period of 1. Now this is ky equals 2. So now if we go here, from here to here, that's a period of 1/2, right? So the period has decreased by 2. And if we go here, ky equals 4, now from here to here, that's even halved again. And so you can sort of see as I keep one spatial frequency constant and change the other one, I'm essentially not only changing the period in the y direction, but you can also notice that the k vector is changing. So it's here, the perpendicular is here, right? So that's like the vector 4, 1. Now the period, the direction of propagation is here. So this is like the vector 4, 2. And here at a 45-degree angle, I'm propagating here. And that makes sense because kx and ky are both 4. So I'm just propagating along a vector like 4, 4. Okay? So that's important to keep in mind, that essentially the direction of propagation of the wave is essentially going to be given by the coordinates. If you wrote like 4, 2 and wrote a vector that 4, 2, that would give you exactly the propagation of these wavefronts. Okay, let's see if there's any questions. No questions. Okay, so we'll keep going. Okay, so the next concept that we're going to spend some time on, and that's really important, and if you get a good sense of this, then you know the MRI part. This will certainly be helpful for understanding MRI a little better. But in general, this is useful for anything that uses Fourier transforms. So if we have something in image space, so here indexed by x and y, it's a function of x and y, and we take its Fourier transform and we get something that's a function now of kx and ky, then we also, a very common term for this is just k-space. And so when we talk about moving in k-space in MRI, we're talking about sort of how do we collect data moving through this space, and we call this k-space. So we want to spend some time getting familiar with what k-space looks like. And so here is k-space. And so this would be kx axis. This would be the ky axis, okay? And let's say we take a point here and we say, okay, the brightness in this k-space says there's some component here that has there's some energy or some amplitude of a component along here. Kx has some value, ky equals 0. Right, so ky equals 0. So we know we're talking about a component that only varies along the x direction, okay? And it varies with some period. Now we move along the kx axis to some point farther out in k-space. Now this has a larger value of kx. So anything with energy out here would correspond to energy that's represented by something with a smaller period, all right? So anything here along this axis here, if there's, so here, this is black, so meaning the signal doesn't really have any energy out here at these high frequencies. It's only at these relatively low frequencies that we have contributions for terms like this. So we had a very high frequency term out here, it would correspond to some black value, which means that there's really not much contribution of that frequency. And you'll see something similar in your homework assignment. You'll see your k-space will look very much something like this. Similarly, if we go along the ky axis, we go out to some point here, it's going to have variation only in the y direction. And it has some period. And if we go farther out, then as the farther we go out to k-space, the smaller the period is. All right. And finally, if we go out here, essentially at a 45-degree angle, we know that the wave is going to propagate in a direction that's perpendicular to this vector. So the vector is from 0 to this point is this, right? And that's represented by this thing here, okay? And so this is a component here that corresponds to this k-space location. So basically, look, depending on, like, if you see something in your signal that varies this way, you'll say, well, it's probably coming from this part in k-space. If If you see something in your signal that varies here, it's going to correspond to something in this part of K-space or in this part of K-space. You can't really tell because both of these would sort of have a particular component. And if you see something varying like this, you know it's got to come from somewhere along the KY, or the KX axis. Okay, so how do we make up our image? So we've talked a little about K-space. So we know that and we're arguing that any image can be made up of a bunch of sort of these patterns of spatially varying cosines of different frequencies and also different directions. And so this is an example of here in this row, I'm showing what Fourier component I'm adding to my image. Okay, so you see I add something that varies this way, varies this way, varies this way, varies this way, varies this way. Here in the second row, I'm showing what the corresponding image looks like. Okay. And so as you sort of see, even if I've just added these 5 components together, I'm sort of getting something that you can sort of tell, you know, is some sort of blob. You're not really sure it's a head or even if it's a human yet, but it looks like it could be a head. As I add more and more of these components here, okay, and you see they have different frequencies and different spatial orientations, I slowly build up the images, okay? And so I go for something that's fairly low resolution, and as I add components with higher and higher frequencies, I end up with a reasonable looking image, okay? So this is showing the idea of how we're taking any image and building it up from a summation of different sines and cosine patterns in X and Y. So let's see if this image plays. Hopefully this will work. Uh-oh, let me change this screen interruption to visible. Okay, great, so this does play. So what I'm gonna do is I'm gonna let it play and then I'll explain what we're gonna see, okay? So let's bring it back to the beginning. So what we're doing here is we're filling in K-space. So we're just starting off with some middle part of K-space. So the middle of K-space represents the very low spatially varying components of your image. So it's very blurry, low frequency components. And so if this is all we have in K-space, and this is the center of K-space near Kx equals 0, Ky equals 0, you see I have a very blurry image, okay? As I collect more of K-space, now I start filling in some details. So you can already tell it's a person, right? Just by adding in enough Fourier components. But you have a lot of artifacts here still, right? There's this weird ringing, like this person's brain doesn't actually have these ringing in it, right? And there's weird stuff coming off their skull. And so this, you know it's a head, but you probably wouldn't want to make any diagnostic decisions based upon this image, right? So we go ahead and collect more K-space. Okay, here, that's a lot better. I can start seeing the structures in the head here. I see the cerebellum, the corpus callosum, the brainstem. I see the cortex pretty well, but there's still quite a bit of artifacts here. Like there's these ridges here. There's still a bit of ringing out here, right? So this might be good enough if there was a big tumor, but if there was a very tiny tumor, I might not be okay with this image because there's still some stuff here that's sort of getting in the way. So I would collect more of K-space. That looks pretty good. A lot of those artifacts are gone. There's nothing really left out here around the head. And so I can go off and collect all of K-space. And at the end, I have a pretty good looking image. So you can sort of see that there's a trade-off between how much of K-space I collect and what the image looks like. And part of what we'll cover when we talk about MRI is what's good enough. Like, is this good enough? Is this good enough? Is this good enough? And what's good enough depends on the application. This probably, you know, you don't have to be a radiologist to know that this probably is not good enough, but this might be good enough, right? And maybe this is too good, and maybe this is too good. And why would you want not to collect all of data? Well, because it takes time to collect this data. So you want to make a trade-off between what's a good enough looking image and how much time do you want to spend collecting the data, all right? Okay, so we're going to go through some exercises together, and then we're going to open up there's only a few of you on, but we'll still do a poll just so you can respond. So this is the image. I believe this is the image that's in homework 4. So I think, and some of these exercises probably are in homework 4 as well. So the answers you get should look very similar to this. So if you watch this video, I think the exercise 2 in homework 4 should be fairly straightforward for you. So what we have is our image, and this is its Fourier transform. And now I'm going to play a game where I just basically mathematically just zero out all these components here. Okay, so I keep all the data, but I'm only keeping this data here in this strip. So what I've done is I've sort of eliminated all these points here along the kx axis, for example. So what that means is if you, unfortunately, I can't really zoom in on this with this display right now. But what that means is, and if you look at this sort of on your, on the PDF that's downloaded, you can zoom in on it. But imagine I'm sort of traveling in the x direction, right? If I look at this structure here, this is the corpus callosum, so and this is the brainstem. So you notice it's a very sharp edge here, right? And here, that edge has gotten sort of less sharp going in this direction. Okay. And similarly, you see these really beautiful fine details here moving along this direction, right? These like vertical lines here in the cerebellum, almost vertical, they're basically gone here, right? Because I don't really have information to represent variations going along the x direction. I've also lost a lot of information out here for some of the diagonal elements too. So that's lost. Now, what I have preserved is imagine if I go in the y direction, this edge here, which is an edge that I would meet if I'm going up and down, that's still fairly well preserved because I've kept all the information along the ky axis, okay? So this is sort of showing how the information I have in k space is related to what the image looks like. So here we play the game where now I've gotten rid of all of this data and I'm only keeping the values here, okay, along kx. So now this here, it's not great, but I am sort of getting back some of those structures, right, that I would hit as I moved it in this direction. But notice as I move in this direction, this edge now that was very sharp is very blurry now, okay? And similarly, this structure here, this very fine structure here, which I would sort of see that structure if I was moving in this direction, it's basically blurred out, right? So I'm really losing any information going along this direction, but I have some information going along here. For example, this edge here is very sharp, right? So as I move along in this direction, I'm preserving that sharp edge, but I've lost this sharp edge, okay? And in this example here, I've blacked out all the data at high frequencies and only kept low frequencies. And so this is basically blurred in both directions. So it's blurry this way and this way. And basically any direction you go, you've really lost a lot of the fine detail. I really can't see any of those finger patterns here at all. And all the edges sort of look blurry. And that's very common. And so this is sort of what it looks like if I only keep low frequency data. This is just the same thing here. This is the full stuff. Now I'm playing another game where I only keep information out here and I've zeroed out all this information. So I've basically gotten rid of a lot of the low frequency information. So really the information I have is along mostly the kx direction. And so here you see I preserve the edges as I move along in the x direction, right? So those edges still exist, but I've mostly lost the edges that I would hit if I moved along the y direction. Okay. And similarly here, I'm only keeping this information and I've lost this information here. So as I go along the y direction, I still see those edges pretty well, but I've really lost a lot of the edges going along the x direction. Okay. Now here I've kept all the edges both along kx and ky. And so you sort of see I preserve the edges both in this direction and that direction. So what that means is the outer parts of k space, those are essentially the edges in your image, okay? So always think about the inner part of k space as sort of your low frequency, sort of the overall shape of your object. And then the outer part of k space is what you're going to use to fill in the details of your image. Okay, and then I think, okay, we have one more thing we're going to do before we go to a poll. Here I've added some, energy, a component out here in K-space. And so the corresponding image looks like this, right? So this is a spike of amplitude here. And remember, if I take a line and draw a vector from the center of K-space out to that point, then the waves would propagate perpendicular to that vector. And in fact, that's what it looks like here. All the interference patterns are a wavefront moving in this direction, okay? Because it's along the KY axis. So it makes sense that the added interference just is along the Y direction. Now I've added a component here that's off diagonal. It's a diagonal point, has both KX and KY. And I think of drawing a vector from here to here, this would represent components that are perpendicular to that vector. And in fact, this is what I see here. The interference pattern is moving along in this direction, which is exactly the direction of my, where my K-space component is located. Okay, so what we're going to do now is we are going to, let's see, pointer options. Whoops, what happened to my pointer? Uh-oh, lost my pointer. Hold on just a minute. Where is my pointer? So I can escape out of that. All right, let's try that again. Pointer options. Visible, okay. So I'm going to start a poll. Let's see, I think. Okay, so let's just, this is an arbitrary multiple choice. So let me explain what we're gonna do. And there's only a handful of you. So just this is more so I can get a sense of where people are at. So here I have 4 different images, A, B, C, D. Actually, since there's only a few of you, let's just use a chat for this. That'll be better since we can then do the whole thing. So for example, and you can send it to everyone or just send it to me. It doesn't really matter. I'm just trying to get a sense of where people are in case we need to review things. So A corresponds to this. So this is your image. This is your Fourier space. And these are different images, B, C, and D. And these are the corresponding 1, 2, and 3. So basically you want to match B to either 1, 2, or 3, C to either 1, 2, or 3, and D to either 1, 2, 3. So go ahead and take a look at this. And essentially in your answer, you can just say B goes to 1 or B goes to 2, C goes to 1, D goes to 3, and so on and so forth. All right. So why don't we take a minute or so? I'm going to just stop my video for a minute. I'll take a little break, and then we will reconvene in about 2 minutes. And in the meantime, just submit your best guesses. This is really not graded. It's just so I get a sense of where people are at. Okay. So take a minute or two and then submit your answers. Okay, so a couple of people have answered. So the remaining two of you, if you could just go ahead and just put in your best guesses, that'll be great. Thanks. Okay, so let's proceed. Not sure everyone's still there, but we'll proceed anyways. So let's look at talk a little bit about how to do these sorts of problems. So there's three different images here, B, C, and D. So which of these has the most sort of information or details? So just enter into the chat. Is it B, C, or D? Right, so I have one answer. So D does seem like it has the most information, right? So then in of 1, 2, and 3, which one has the most sort of parts of K-space? Is it 1, 2, or 3? Yep, that's 1. So clearly D goes with 1, and so I think most people got that. So then the question is really, does C go with 2, or does C go with 3, and also for B, the same thing, okay? Great, so let's look at C. So C has variations. If I move along the X direction, let me get my mouse back on here, screen options, laser pointer. If I move along in the X direction, I'm clearly running across edges, right? And I lost the edges if I move in the Y direction. So therefore, since I'm hitting edges as I move along in the X direction, I must have energy out along the KX axis. So therefore, I must be this guy here. If there's a choice between 2 and 3, this clearly has energy along the KX axis where this does not, okay? So I would go, C would go with 3, and therefore by process of elimination, B would go with 2, right? But let's just check that. The B, I'm clearly hitting edges as I move along this direction, right? And whether I'm hitting edges this way or not, it's hard to tell, but they're certainly, if I am, they're certainly not as strong as the edges I'm hitting in this direction. So therefore, it makes sense that this has a lot of information about edges along the KY axis, okay? So therefore, these components here correspond to edges that I hit moving along the Y direction, okay? So B would go with 2 for that. So any questions on that before we proceed? Okay. All right. Yeah, there's 2 more exercises to do, and I think same thing. Let's go ahead and do this one. And so take a look at this. 1, 2, and 3, A, B, or C, and just take a minute or so and look at this, and then submit your answers. Okay. Okay, in the interest of time, let's take a look at this. So yeah, I think those of you who responded seem like you have a pretty good sense of this, although there's something we do need to make sure we get correct. So I think the answer is both of the people who submitted both had 3 with A, and that makes sense because obviously A is the worst looking of these images, right? It has almost no edges, whereas each of these has a little more information. And so that would correspond with what has the least amount of information in Fourier domain. So definitely 3 would go with A. Now, what takes a little more time that we need to discuss is, does 2 go with C or B? Okay, so let's think about that. Here we're keeping information along the KY axis, right? There's definitely information along the KY axis, right? So that would correspond to edges that we would hit as we're moving along the Y direction. So B arguably doesn't really have that edge, whereas C does have that edge. So therefore, C would go with 2, okay? And so that's something that is confusing to some people. So it's useful to think about, there's 2 ways you can think about it. One, if something has something on KY axis, know that it corresponds to edges propagating in this direction. And so that would be that, okay? The other way you can think about it is it corresponds to, if all in KY direction, then the edges are perpendicular to that. And so that's these edges here. And similarly here, we have data energy along the KX axis. So that corresponds to edges that are perpendicular to that, which would be edges up, down, or edges that we hit as we move in the X direction. And so here, these are up, down edges or edges that we hit as we're moving along the X direction. All right. Let's see. Okay. In the interest of time, we're actually going to skip this example, although I would highly recommend you do this on your own. And if you have questions, feel free to ask me about it. But this is a little trickier, but I think in the interest of time, we're going to cover some more material, okay? Because I do want to spend some time that's for your homework that will be helpful in terms of how do you compute transforms. So some of this was covered already in Professor McVeigh's lecture. So we're going to review some of it and then introduce some new material. So first of all, we're going to go over some very common transforms that are just good to memorize. The first one is that the Fourier transform of a Dirac delta function is just 1. Okay, so that's very useful to know. And it's just obtained from the sifting property of the Dirac delta function. Anytime I multiply a function by the Dirac delta and integrate it, I just pick out the value where the Dirac delta is not equal to 0. And so in this case, that's x equals 0. So e to the 0 is just 1. Similarly, if I take a shifted Dirac delta function, I would just end up with a composite exponential here because I'm just picking the value and substituting x0 for x here, okay? The other really important function for this course is the Fourier transform of a rect function. So remember, this is just a function that takes on value from -1/2 to 1/2. It's 1 there, and it's 0 everywhere else. And so just from first year calculus, you can sort of do this integral. It's an integral of an exponential, and it turns out to be sine of pi kx over pi kx. And this is such an important function, we give it a name. It's called sinc of kx, okay? So this is a useful function to get to know, and we'll take a look at it more in the course as we go along. Now, one sort of thing that's sort of hard is, what is the Fourier transform of 1? And if you just actually plug in definition, it's not so obvious what the answer is, because how do you actually evaluate this from -infinity to infinity, right? What is e to the, if you evaluate this, you're going to get e to the something of x with some other stuff. And what's e to the -j infinity? It's really not well defined. So it turns out that the way to define what this turned out to be a generalized function. So you actually have to see what it does under an integral. And it turns out that this function, if we define h of kx as this function and we put it under an integral, it basically sifts out the value at kx equals 0 and gives you g of 0. So therefore, it acts like a delta function. And so therefore, we say that the Fourier transform of 1 is equal to the delta function. So that's useful to keep in mind. And so, for example, something that, let me see if I can get the pen going here. Right. So if I have 1, right, that goes to the delta function, right? And then delta, sorry, that's not a good very delta, but you get the point, goes to 1, right? Hopefully I'll get my iPad working for next time. All right, so that's a useful Fourier transform pair just to commit to memory. 1 goes to delta and delta goes to 1. Similarly, if I have a complex exponential, it's basically just a drag at k0. And this is, the way to remember this is, this has a frequency of k0, right? So in Fourier space, it's represented as just a component that only has value at k sub 0, okay? Similarly, I can take f of cosine 2 pi k naught x, and this is gonna be, if I expand this out, it's got e to the j 2 pi k naught x plus e to the minus j 2 pi k naught x. So it has values both at k naught, so this has a value at k naught, and this has a value at minus k naught. So it's got, if I were to draw the spectrum, it would look something like this. Let me get my pointer option again. So this was kx, right? I would have a delta function here and 1 here, okay? At k0 and minus k0. And both of these would have value of a half. Okay, and similarly for sine, except now you have a minus, this would be a minus thing with a 1 over 2j associated with it, all right? So these are also very important to keep in mind. And the way to keep in mind these is just anytime you see something cosine or exponential, look for this term. So 2 pi, and this is the frequency term, right? So you can rewrite everything as 2 pi something times x, and then you pick out this term, you know, that's your frequency, and that's where you're going to have your delta functions, all right? So especially if you're not too familiar with this, it's useful to have some sort of little hints that can help you guide you through your homeworks and quizzes. Okay, so let's take a look at what this means. So basically, this is just showing that, for example, this is taking a cosine function and splitting it into these two complex exponentials. And the point here is this is positive kx here, and this is a minus kx. So there's a minus term here, okay? And so what's the difference? Well, the positive kx, e to the j 2 pi kx x, this has a positive phase as I move along in the x direction. So if you notice that this blue thing, there's a blue one here, and its phase goes from here to here to here. So its phase, theta, is getting more positive as I move along in the x direction. Whereas this one, the red curve here, its phase is going in the clockwise direction. So it's becoming more negative as I move in the x direction. So that's what we mean by positive and negative frequencies, which is sort of a strange term. So, you know, so this has a positive frequency kx, so that means its phase is going to be going counterclockwise as I move in the x direction. And then this is a negative kx, so this is what we call a negative frequency. And it's the same spatial frequency, but it just moves in a different direction. And the summation of those two, because those phases go in opposite directions, the imaginary parts cancel out and we're just left with the real part. So that's why these two complex exponentials added together just give you this green thing, which is always a real term. And it's shown here as cosine 2 pi kxx. Okay, and here kx equals 0.1. So that means the period is 10. So if I go from here, minus 5 to 5, that is a period of 10. That's shown here, and I believe this is maybe the MATLAB code was online for this, but basically showing kx equals 0.1. You sort of the phase is curving around like this, so it's moving in a counterclockwise direction as I move along in x, and here we're moving in a clockwise direction. All right. Okay, and the summation of these two just gives you something that's real. Okay, so this is basically the real, supplying the real part and the imaginary part here, and this is the x direction, and just sort of showing that's a phasor moving around like this in one direction, or a phasor moving in the other direction. If I sum these two up, then I only get this cosine term that's always real and just looks like the cosine and only has real terms. Okay. One important concept that we'll cover later in class is that the Fourier transform exhibits what's called conjugate symmetry, which means, let's say I know the Fourier transform of at some frequency g of kx. It turns out that, and I also know the Fourier transform of at a negative frequency, okay? Well, these terms look very similar, right? I mean, they're almost the same expression. So we would expect that there's some relationship between this term and this term. And it turns out if g of x is a real function, then it satisfies what's called Hermitian symmetry, which is g of kx is just a composite conjugate of g of minus kx. And we'll see later on in MRI that this is useful because it allows you to save time. You don't have to go through all of K-space. You can maybe just collect part of K-space and then estimate the rest of K-space using this complex, this Hermitian symmetry. This also applies in 2D. If I know g of kx ky, then I can say that's also the composite conjugate of g of minus kx minus ky. And so in this case, information in one area of K-space gives me information about another area of K-space. So I don't necessarily need to collect all of K-space, which can save me time. I think we'll skip this one for now. It's not too important. The other thing that you'll find very useful as you're doing your problems is duality. Professor McVeigh talked about this a little bit, but we know that the Fourier transform of this, so this has remember, this has a frequency of A, right? So it's going to be a Dirac delta located at A. And we also know that if I take the Fourier transform of this guy, it equals this, right? So this term and this term look sort of similar, right? They have similar forms. So this is a specific case of duality, where if I know the Fourier transform of one thing, then I can estimate I can figure out the Fourier transform going the other way, okay? The most simplest case we saw that was already a 1 going to a delta or a delta going to a 1. Specifically, a specific case of duality is, in general, is written as this, that if I know the Fourier transform g of kx, and then I plug in x, then I can write the Fourier transform of that function in that case. So the most important case of duality for this course is what is the Fourier transform of a sinc function, right? So to do that by scratch, you'd have to take sine of pi x over pi x, multiply it by this, and integrate that. Now, while that's doable, it would probably take quite a bit of time, and it may not be that easy. But we know from duality, we know that rect goes to sinc. So we can just say, well, if I have a function pi of x, then that should just go to sinc of kx. Okay, so recall Fourier transform of pi of x, of rect of x goes to sinc of kx. So therefore, if I take sinc of x, kx, and replace the kx by x, and take the Fourier transform of sinc of x, that equals the rect of minus kx, according to the formula. But rect is symmetric, so that's just equal to rect of kx. And so that's really important. So the other very important duality is rect function goes to sinc, and sinc function goes to rect. So that's the other really important thing to keep in mind. Rect and sinc are a dual pair. Okay, so either way, so we'll be doing a lot of that in class. So just commit that to memory. A rect goes to a sinc, and a sinc goes to a rect. One thing that trips people up quite a bit is what we mean by separable functions. So separable function just means if I have some arbitrary function g of xy, it's separable if I can write it as a function of gx and gy. Okay. So if that's the case, then g of kx ky equals the Fourier transform of my x object in the kx direct along kx and the Fourier transform of my y. So I can take the Fourier transform of these functions separately and then just multiply them together. Okay, so for example, g of xy, if it's a two-dimensional rect function, I know that the Fourier transform is just the Fourier transform of pi of x, which is equal to sinc kx, times the Fourier transform of pi of y, which is sinc ky. Now, a word of warning, let's say I had g of x, okay, equals f of x times h of x. Okay. Now in this case, they're both x's, right? They're both have both x's. So it's not x and y. So this would not apply because these are both x. And in this case, we'll see later, we're going to have to use the convolution theorem for this. Okay. So this is not separable because it's x here and x here. So this is not where this theorem would apply. This theorem only applies if you can write it as a function of x and a function of y. So this is an example of that. So essentially, this is my two-dimensional rect function, and this is my two-dimensional sinc function. Okay. Okay, so the question is this function separable, and what is its Fourier transform? So why don't we try a poll on this? Let me go back to my pointer option. This is useful enough to look at. So see what's going on here. Okay, well let's just skip that for now. That doesn't seem to be working. So the question is this separable or not, and what is this Fourier transform? So unfortunately, I don't have my iPad here, so it's going to be hard to write this out. But let me just walk you through this. It turns out this is separable, right? Because we can write this as a function of x. We can split this exponential into x and y, and so we could break this into something that's e to the minus j 2 pi 8 x times the sine of 28 pi x times e to the minus j 2 pi 9y. So it's separable, and therefore we could take the Fourier transform of both the x part separately from the y part on its own. These are some examples. So for example, g of xy is equal to delta xy equals delta x delta y. So the Fourier transform of this is 1, and the Fourier transform of this is 1. So 1 times 1 just equals 1. This is sort of tricky. What if gxy equals delta of x? Well, this is actually g of xy delta x times 1, right? So to do this, delta of x goes to 1, right? This would go to 1. And this would go to my delta ky. Okay, so the multiple of these is delta ky. So that's sort of a trick question there. Okay, an important part of K-space is the center of K-space. So essentially, and this will be useful in a future homework, essentially, if I put 0 in here, this term just goes to 1, right? So this just goes to 1. And so I just have the area under my curve. Okay, so this is area of g of x, and in 2D is area of gx, gy integrated over dx dy. And so the center of K-space is always really just the mean value of your function. You basically integrate the function. And so the center of K-space tells you a lot about, how much, what sort of the mean value of the function is. And so typically for like a brain or a body, it's the average, and it basically tells you the average amount of how many spins, how many protons are in your object. Okay. A couple of things you should know about the Fourier transform is it's linear. So if I know by function a times g plus b times h, then I can write by linearity that the Fourier transform is ag plus bh. Okay, so anytime you have weighted function, weighted sum of different functions, you can write its Fourier transform fairly easily. This is some example here. So for example, here I have g of x equals 1 plus e to the minus j 2 pi ax. So I can say that the 1 goes to my delta function, and the e to the minus j 2x, remember this is multiplied by sort of an intrinsic 1. So So this goes to me delta kx plus a times delta ky, all right? One really important part that we'll use throughout the course is the scaling theorem. So that says if I take a function g and I write it as g of ax, then its Fourier transform is 1 over a g of kx over a. So here's an important example of that. So here's rect of x here, okay? And now this is rect of 3x, right? So I basically shrinking the function in the x direction, right? So this has width of 1, right? And this would have width of 1/3, okay? So according to this theorem, we know that rect goes to sinc, okay? So this says rect of 3x will go to 1/3 sinc of kx over 3. And so we reduce the height of this, but we also stretch it out by a factor of a third, okay? So this is actually a stretched out version of this sinc function. So this is sort of what's related to what's called the uncertainty principle, which is basically anytime you squeeze something in one dimension, you expand it in another dimension. And so we saw this with sampling, essentially. If you sample more finely in one dimension, you spread out the sort of the impulse train in the other dimension. And that reduces the sort of the aliasing, okay? Okay, so these are some useful facts that just, that we went over. This is from the table in the book. So the last thing we're going to go over in the last 10 minutes is just the convolution theorem, which is actually fairly important. So I want to make sure we cover that and then before we end for today. So in class, you sort of, Professor McVeigh sort of talked about point spread functions, or in this case, a line spread function. It's sort of the same thing. And in fact, I think you're looking at some of this for your CT homework that's due later today. So for example, here would be point spread function. So here, it's fairly narrow and it's getting broader and broader, right? And so we know that as things shrink in this domain, so this is getting wider in this domain, if we look at its Fourier transform, which is known as the modulation transfer function, it should be getting narrower. And in fact, it is, okay? And so the point spread function is getting broader, so it's becoming more blurry. And then its Fourier transform is shrinking, which means that we're lacking a lot of these high frequency components now, right? And that makes sense because if my point fraction is very sharp, right, then I have a lot of high frequency information that I should have a very good representation of my image. If my point fraction is very broad, it's going to blur out anything, and it's going to get rid of all these high frequency components. So one way you could test these things, for example, is you could have, instead of just a point object, you could have a bunch of test phantoms which have varying frequencies. Here's two sort of patterns that people use, and just sort of see at what frequency you can no longer tell what's going on. So the modulation transfer response is essentially what's the response of your system to every frequency. And so in this case, for example, if I have a frequency of 1/2, it responds fairly well. But as I increase the frequency, notice that the response of my function, which is shown by the distance here between these two lines, it's going from 1 to 68, or sort of 100 to 68, 100 to 48, 100 to 27. And then here, at a frequency of 3, I've really reduced the response of my function. So in this case, the frequency response is falling off as I go to higher frequencies. And so I plot that as a function of frequency and plot those amplitudes. That's essentially modulation transfer function, okay? And one of the most important things is just to remember that that is essentially the Fourier transform of your impulse response. So this is shown here where we have A, B, and C as different impulse responses. And so clearly C is the narrowest impulse response. So C would correspond to 3 here, okay, which has the broadest modulation transfer function. And similarly, A is the broadest point spread function. So it would correspond to 1, which has the narrowest one, okay? Okay, and then the final thing we want to talk about is Fourier transform of convolution. So remember, what we do a lot in linear systems is we might want to convolve two functions. And notice in this case, they're both a function of x. Okay, so this is taking two functions of the same underlying variable x and convolving them. And it turns out if I want to know the Fourier transform of this. And it turns out it has a very nice form. It's just g of kx times h of kx. Okay. So now this is different from what's separability, where before we had gx and h of y, and then we had g of kx, h of ky. So this is different. So it's important to keep that in mind. We also have the dual, which is if I have two functions, g of x and h of x. And notice this is not separable anymore because these are both functions of x, right? That's a function of x, and this is a function of x, right? So now we get g of kx convolved with h of kx. So that's very different from the separability theorem we went through before. So we're not going to go through this in too much detail, but I'm just going to give you some examples of how to think about this, and we'll cover it more in class later. The convolution theorem we can think about we can take any signal and can decompose it into Fourier components like we saw before. And so it might have some Fourier transform like this. And we imagine passing this through something with the modulation transfer function or an impulse response like this, which would have some modulation transfer function. So this tells me how to weight each of these components, right? So something like this going through a linear system, linear time invariant system, the output is just going to be g of t convolved with h of t, which is my impulse response. Okay. But that's similar to taking each of these components and weighting them by this modulation transfer function, right? So I know that the Fourier transform is just my input Fourier transform multiplied by the Fourier transform of my impulse response. Essentially, that's the convolution theorem. So I have convolution in the time domain, I have multiplication in the Fourier domain. Okay. We can skip that for now. This is sort of, you could read this on your own. It's just sort of giving more background on this. Let's do an application of the convolution theorem, and I think we'll end hopefully on time. So let's say you're given this function. This is a triangle function. It's 1 minus absolute value of x for x less than 1, 0 otherwise. So this is what that function looks like, right? And to do the Fourier transform, you'd have to solve this integral, okay? Which is doable, but might take quite a bit of time to do, okay? So the trick is to realize, well, I could get this function. If you go from the supplementary session 1, we realize that this is just a convolution of two functions. The rect function convolved with itself. So the triangle function equals a rect function involved with another rect function. Therefore, by inspection, we can say the Fourier transform of this triangle function is just the Fourier transform of this, which is sinc, multiplied by the Fourier transform of this, which is sinc. So we get the Fourier transform of a triangle function is just sinc squared kx. All right. So in your homework 4, you'll have opportunities to sort of make use of this property, where essentially if you see convolution in one domain, you know it's multiplication in another domain. If you see multiplication in one domain, it's going to be convolution in the other domain. So that's, I think, all 4 problems on homework 4, part 1 are application of this property. Same thing applies to 2D, but it's a little harder to do things in 2D. So typically we do that in MATLAB, but here's an example of that. So for example, here, I have my object g of kx, right? So it's a rect function. And I'm going to convolve it with this sinc function, okay? And this is my impulse response, okay? And if I convolve these two together, essentially I replace every dot here with this impulse response, and I get a blurred out version of my object. So it's this convolution in this domain here, okay? So this is g of xy convolved with mxy gives me this. So that's this convolution shown here, okay? So that means in the other domain, I know the Fourier transform of a rect function is just a sinc, and the Fourier transform of a sinc function is direct. So in this domain, I know I'm just going to multiply. So I just take this two-dimensional sinc function multiply by a two-dimensional rect function. And this rect function basically only keeps stuff in this regime and zeroes out everything else. And so I'm just left with this. And so in fact, this truncated sinc function has a Fourier transform that looks like that. So we're going to find this very useful when we talk about MR, because typically, let's say this is all of K space, and you say, if I had enough time, I'd collect all of K space. But in fact, I only have time to collect K space in a certain region. And that's represented by just taking this and multiplying it by this. And so I only collect this much K space. So it means the effect on my image is I take my image, my high quality image, I'm convolving it with the Fourier transform, the inverse transform of this rect function, and that's to make me a blurred out image. Okay. Let's see. So one thing to notice is if I have, because of, let's say I have different modules in a system, each with its own impulse response, the output will be the convolution of all of these. So I convolve this with this, the output gets convolved with this, and then convolve this with that. So in one domain I'm convolving, that means in the other domain I'm just multiplying these spectrum. And so imagine if I did that, let's say I have the spectrum for A, B, and C, you can see I'll be dominated by this A, right? So if I were to try to improve the system, the overall system has this function, right? Because it's A times B times C in the Fourier domain. So what this says is I really shouldn't spend too much money on improving C, right? Because I'm still dominated by A. So if we want to improve the system, I'm best off by spending money improving system A. And finally, modulation. If I take any function and multiply it by a complex exponential, I'm just sort of shifting it in the Fourier domain. An example of that is AM radio, where I take my spectrum and I just shift it out to different frequencies. In image domain, if I take my object and I multiply it by some exponential function here, or this cosine, I get this sort of funky looking image. In the Fourier domain, that's taking my sinc. The Fourier transform of this would have two delta functions, which are hard to see, and I just shift this to two different spaces, okay? And finally, the shift theorem says if I take any object and just shift it, I get my Fourier transform back just with some complex phase, right? So anyways, we've gone through a lot. The main things to remember from this supplementary section, I mean, you can take your time to review this video, and you can also look at last year's video where I sort of had the iPad and went through it in a slightly different format. But hopefully you have a better understanding of K-space and understand what the patterns are in K-space. And then you should have some working knowledge of Fourier transform pairs, and also some working knowledge of sort of these scaling theorems. And then the most important things that we'll use often over and over are the convolution and multiplication properties. So when we convolve in one domain, multiply in the other domain. So I think with that, you should be a little better off in terms of being able to do the homeworks and also sort of understand the material on MRI. So I know we're at the end of our time, so let me know if there's any questions. Otherwise, we will end pretty much on time. Okay, I'm not seeing any more questions, so I'm going to stop the recording.